Greetings, dear audience. My name is Stefan. I am Sales and Application Engineer for laser products at iC-Haus. In this hands-on video, I will go through the process of getting started with the iC-NZN evaluation board. The iC-NZN chip in the center of this board is a very versatile closed-loop single-channel pulsed and CW driver for laser diodes. The iC-NZN can be operated in ACC, automatic current control mode, or in APC, automatic power control mode. In the case of automatic power control, a photodiode is needed as feedback. For more details about the differences, see our tech talk on understanding control concepts. Let's have a look at the pieces that are needed for basic evaluation of the iC-NZN's functionality. Most importantly, it is of course the iC-NZN EVAL NZN1D board. Secondly, instead of a laser diode, I brought a more versatile replacement. This dummy has an infrared LED and a photodiode, so it replaces a laser diode with a monitor diode integrated in its housing. It gives me more flexibility to show things. For example, what happens when light stops to hit the photodiode. The wiring of the LED and the photodiode matches the N-type pin configuration that is ideal for the iC-NZN. The iC-NZN can be pulsed. To show this, the iC-213 oscillator is an alternative to a function generator. The iC-213 fits directly onto the J1 socket of the NZN1D. To visualize the turn on and the transient response of the system, I recommend a fast photoreceiver like the iC-212. This variant is matching with the wavelengths of the LED. And to correlate the different signals, a pretty standard lab oscilloscope. Last but not least, a set of resistors, jumpers and possibly capacitors to experiment with different set points and time constants of the feedback loop. Besides these equipment prerequisites, some mental work should be done before plugging in all the parts. Studying the datasheet of the NZN should be part of your preparations. It contains also the schematics of the NZN1D evaluation board. Drawing out the current path of the laser circuit and tracing the connections from the configuration pins to the sources helps to set the required jumpers. Carrying out the calculations to derive the required resistor values in the control loop and the current monitor to match with the used light source and photodiode will prepare you to exchange parts if need be. With these basic remarks out of the way, let's go to prepare the NZN1D for running in APC. Here are the schematics for the NZN1D evaluation board. Highlighted is the current path starting from the supply voltage at terminal VDD through the iC-NZN and of course through the N-type laser diode, including its monitor diode. At 3 points there are jumpers that need to be set. Starting from the bottom, JP1, a 3-pin jumper, needs to be set connecting pins 1 and 2. As a control mode is APC with a N-type pin configuration. On the PCB, JP1 is in the center to the right between the iC-NZN chip and the potentiometer besides it. For connecting 1 and 2, the jumper sits on the lower position. JP2, also a 3-pin jumper, needs to be set connecting pins 2 and 3. This is for APC, of course. It connects the sensing pin MD of the iC-NZN to the monitor diode's current path. JP3 is found top left of the iC-NZN. And the jumper is closed. This covered the jumper settings for APC with an N-type laser diode. You will have noticed that there are other parts connected in the laser diode circuit. Down here, the resistor R1 and the potentiometer P1 form the resistance of the monitor circuit. In the documentation for the iC-NZN, their combined value is often referred to as RMON or RMD and PMD when they are mentioned individually. The NZN1D has a fixed 5.1 kilo ohm resistor and a potentiometer in series to it with up to 10 kilo ohm. So 5 to 15 kilo ohm can be set as R1. The control loop aims to have a voltage drop of 0.5 volts across RMON. This gives us a range from 33 microamps to 100 microamps of monitor current, which can fulfill this condition. This monitor current range should overlap with a typical photodiode output of the laser diode you selected. If it does not, change the fixed resistor at socket R1 to another value that yields a matching monitor current range. The monitor current for the laser dummy is also expected to be in the microamps region. This should work now. Besides the monitor resistor, the current limiter needs to be checked, as it is active on the NZN1D evaluation board by default. Let's have a look. The resistor R2 to the left of the iC-NZN is a 2.7 kilo ohm resistor. With the formulas from the datasheet, it can be calculated that this will limit the current to about 100 milliamps at pin LDA and to about 130 milliamps at pin LDK. Those are slightly different values as there are two different mirror factors involved. The current limit should of course protect the laser diode from a too high current. The LED in the dummy is rated for 100 milliamps, so this limit should be good. That was all what should be considered on the evaluation board before powering it up. At the lab power supply, the voltage for the circuit needs to be set. I set this to 5 volts. That must be at least the sum of the forward voltage or operational voltage of the laser diode plus up to 3 volts due to the saturation voltage of the iC-NZN. If the current monitor and limiter, which is the block LDA monitor in the block diagram, is used, then an additional circa half a volt needs to be added to the supply voltage for best performance. Having prepared everything, it is now time to connect the evaluation board to the power supply. The chip is now active and draws about 5 milliamps of current. The signal of the photoreceiver, which is the green one on the oscilloscope, is still at 0. I have to turn on the channel at the switching input EP. For this, I will use some alligator clip jumper wire to connect terminal EP on the NZN1D at the right-hand side to the VDD terminal at the top left of the NZN1D. Now observe how signal of the LED increased at the fast photoreceiver when the channel was enabled. Nice, the light signal went from 0 millivolt to just below 10 millivolt. And from the power supply I can read that now 80 milliamps are consumed. So the LED on the laser dummy draws about 30 milliamps of current. Let's see what we can do change with the potentiometer. If I turn it clockwise toward the max position, the light output and the current drawn increases. At the highest setting, thus lowest resistance value of 5 kilo ohm, it now reads just below or just around 20 millivolts of signal from the photoreceiver, and the LED draws 25 milliamps of current. That is only a quarter of its nominal rating. To get more power out in APC mode, with this light source plus monitor diode combination, I will have to change the fixed resistor. When I go from 5 kilo ohm to, for example, 2.4 kilo ohm, that will double the monitor current needed for a 0.51 voltage drop. So if I assume the light output and current input of the LED scale roughly in a linear fashion, I might get double the light output with the 2.4 kilo ohm resistor. So I will disconnect the power, reset the potentiometer, replace the resistor, and will be back in a second. The setup is again running, now with a 2.4 kilo ohm resistor, still showing around 10 millivolts from the photoreceiver. Turning again the potentiometer clockwise, approaching the max setting. Now it reads 40 millivolts from the photoreceiver and 50 milliamps current drawn by the LED. The LED is now at roughly 50% of its current rating, a pretty realistic operating point. This is about enough to show how to select a proper ARM-ON. Another feature I want to show is the error handling in case of overcurrent. One common error is to lose the feedback path. I will put this little paper strip in between the LED and the photodiode. When I do so, the feedback signal is lost and will go to 0. The control loop will try to get it back by increasing the current through the laser diode, or here the dummy LED. The check for error LED lit up and the current is limited to the value that was set. And that was set by the resistor RSI. The power supply now reached 110-112 milliamps of current, and the photoreceiver signal went up to around 75 millivolts. As soon as the feedback path is operational again, the current and thus the light output drop again to their nominal levels. That is all what is needed to operate the iC-NZN with automatic power control. Next, I will have a look at the dynamic behavior when the channel is activated using the pin EP. This will make clear how reaching the set point takes different amount of times, and why the value of the CI capacitor needs to be selected. To show how the set point is reached, the oscilloscope will trigger once on a rising signal at terminal EP. I will just connect the terminal EP to the VDD terminal with an alligator clip jumper wire. The rise time of the optical signal was quite fast. One division of the oscilloscope is only 100 nanoseconds, and the rise time of the green trace covers not even half of a single division, so less than 50 nanoseconds rise time. The high level for the optical signal is already reached after those 50 nanoseconds, which is the level that we saw before approximately. That is a quick response, which allows the iC-NZN to be used in pulsed operations. Reason for the quick response is the relatively small internal CI capacitor. So let's have a look how the set point is reached with a much larger external 100 nanofarad capacitor. For this, I close jumper JP6CIX'd near the CID terminal at the lower end of the PCB. I will rearm the oscilloscope for a single trigger with a longer time base and again go from EP floating to VDD by connecting the circuit with an alligator clip. The transient response of the optical power is now very different. The time base of the oscilloscope is now set to 100 microseconds per division. It takes more than 150 microseconds to reach the already known set point. This slow start might be the right choice for many applications. As a next step, I'd like to add pulsing, but the microsecond rise time is slow, definitely too slow for pulsing with 40 kHz. So I will circle back to using the internal CI and add the iC-213 oscillator module configured to a 40 kHz output. Now I will connect the TTL output from the iC-213 oscillator module to the EP input pin at jumper JP12. See how the single trigger captured the beginning of the pulse train. The beginning of the very first pulse is identical to the one I just showed, so I do not need to capture with the 100 nanosecond time base setting again. Instead, the oscilloscope is set to 100 microseconds per division to show the pulse-to-pulse stability. Every pulse has the same form, no drift of pulse height over time. This is a correct CI value for pulsing without averaging. The next function to try out is averaging. For using the averaging function, I will only add the jumper at JP8 and adjust the time scale on the scope. JP8 is here. The relative optical power changed. Peak power should have doubled, but as you see, it is not constant during the pulse. This tells me that the internal CI capacitor is too small. This leads to this huge overshoot at the beginning of each pulse. I will change to the external CI by adding the jumper JP6. Now the overshoot is gone. The capacitor is large enough. Depending on your pulse settings, you will have to experiment a bit to find a well-fitting CI capacitor size. Time to enter into my last section, using automatic current control. To change all the jumper settings to get into ACC mode, I'll disconnect the power supply for a moment. For ACC, JP1 needs to connect 2 and 3, while JP2 needs to be 1, 2. As per the best performance recommendations in the iC-NZN datasheet, I make sure that for ACC the averaging is turned on. Here at JP8 on the evaluation board, the jumper is still set. JP12 is open to disconnect the iC-213. Again, the jumper wire from terminal EP to VDD will do its job. The most work, again, is choosing the right HandsOn value. I aim for about 280 milliamps of current. Calculating from the given formula and a mirror factor of 240 to get the monitor current IMON that is needed in the formula, the result is a resistor with about 430 ohm to be placed at R1 on the evaluation board. Please bear with me while I swap out the resistor. And finally, connect VDD again to the power supply. The light is still off, showing 0 mV at the green line on the oscilloscope. The evaluation board, together with the iC-213, draws 440 milliamps in idle approximately. When I now connect EP to VDD to activate the channel, the light signal goes up to around 20 millivolts. And 20 milliamps are consumed by the LED. Now it is time to turn again the potentiometer, as I reset it to the middle as usual. By going clockwise, I will increase the current and thus the power. I will stop at 520 milliamps in total to not trigger the overcurrent monitor. Now the light signal is again just below 90 millivolts. I just got to 72 millivolts right now. This brightness level will be my starting setup for trying to pulse as fast as the design of the NZN1D allows. For getting the pulsed operation, I remove the alligator clip jumper wire from the terminal EP and connect the iC-213 to it at JP12 using a jumper. I will now go quickly through the frequencies and stop when the pulse shape does not look rectangular anymore. At about 1 MHz, the pulses still look good. But here at 11 MHz, it starts becoming a shark fin. So I can say the board design and its components limit the usable repetition rate to around 11 MHz. This, of course, can be optimized. The Teflon sockets can be removed, for example, and the routing on the PCB itself can also be optimized, as this one is optimized to connect all the terminals and all the exchangeable parts. If the routing is optimized for shorter traces, the highest possible repetition rates will go up. That's it for showing off the basics of the iC-NZN EVAL NZN1D board. More details, especially on the topics not covered in this video, can be found in the datasheet of the iC-NZN, available from our website ic-house.com. So long and goodbye.
iC-House. Integrated circuits.